All right. Thanks, everyone, for coming, and thanks so much to the organizers for letting me speak at this really nice workshop. Today, I'll be talking about some joint work with Isaac Kim on trying to understand the limitations on quantum computing in the near term using tools from quantum many-body physics. All right, so let me first give you a brief summary of our work. So we essentially proved a hardness result on the preparation of low-energy states of lattice Hamiltonians in 2 dimensions. So these are just local Hamiltonians that are very easy to implement on 2D architectures. And they're studied primarily in the condensed matter literature for their properties in terms of long-range entanglement in the ground space, which is sometimes referred to as topological order. And our work in particular was motivated by a lot of the numerical work that's been happening in the literature around variational quantum algorithms. So these are quantum algorithms that you use on NISQ devices in order to estimate the ground state energy of such a Hamiltonian. And so what we were interested in understanding was how efficiently can you do this using methods such as the variational quantum eigensolver. And we found that in general, you cannot expect the convergence of the VQE to be exponentially fast in the depth of your ansatz. Okay, so first let me give you a brief outline of my talk. So first I'll just give a brief recap of quantum computing in the near term and the variational quantum eigensolver. Then I'll briefly state our main result. I'll give you a very high-level proof sketch that will follow 3 steps. And then I'll go into some of the details behind these key components, but this will still be fairly at a high level, so feel free to ask questions about this after. And then I will conclude with some discussion at the end. And if you weren't that interested in the details, it's like the time for you to wake up, I guess. Okay, cool. So first, let's get started on some basics about quantum computing in the near term. I mean, we all know that the devices that are currently around are still fairly limited. They have very few qubits. They're super noisy. For a lot of architectures, you also have only very limited connectivity. So when it comes to superconducting qubits, you're limited to some 2D architecture. And as of now, for most platforms, adaptive circuits are still very hard to perform. This is simply because of the discrepancy between the time taken for measurements and the time taken for gates. So gates are much faster than measurement times. So if you do some sort of mid-circuit measurement and you're waiting for that outcome to be processed, then in the meantime, your qubits just get fried and you can't do anything interesting on them afterwards. But having said that, there are lots of efforts currently in industry to move past that and to actually be able to implement those. So of course, the question then is, with those devices, what do we do since they're already around? And one of the most popular routes of exploration is to try to simply prepare ground states of interesting lattice models. If you want to make your life easier, you might want to just look at gap lattice models, since we know a bit more about the structure of their ground states. So those will be the kinds of Hamiltonians that we're looking at. For those of you who wonder what a lattice Hamiltonian is, well, it's simply just a local Hamiltonian. That means you have some Hamiltonian that you can write as a sum of interactions, where each interaction is just supported on some bounded ball. Okay, so what is this VQE thing that I was just talking about? Well, it's basically just a paradigm to compute ground state energies on near-term devices. I'm pretty sure that most of you have already heard about it, but let me just briefly recap. So your goal is to compute the ground state energy, or to approximate the ground state energy of some Hamiltonian that you'll simply write out in the Pauli basis, which you can always do. And then there is some iterative procedure that couples some noisy small-scale quantum computer to some classical optimizer. And the feedback loop is as follows. So first, you just start, as always, in some product state, say L0 state. You then apply some predefined circuit ansatz, some structured circuit that is parameterized by a couple of continuous parameters that you're allowed to tune. And you simply prepare some trial state psi by applying this ansatz to your product state. Now, you simply perform measurements of Pauli operators that allow you to then estimate the energy of this trial state with respect to your Hamiltonian using classical post-processing. Then you simply apply some classical optimizer, essentially just gradient descent, in order to compute a new set of parameters that hopefully give you a better energy or a lower energy for the next trial state, which uses these updated parameters. Now, at some point, of course, you will plateau for a given circuit depth. And then you have to increase your layer by one more, and you iterate the entire procedure again. This then allows you to have a iterative procedure to get closer and closer to the ground state energy. Of course, on these devices, you don't have any error correction, so you want to do this as fast as possible. And so the natural question is, given that you have some target energy per psilon, how deep must your circuit onsets be in order to reach it or to go below it? Now, there are several different scenarios you might imagine. For example, you might expect that the energy per site just decays polynomially with the depth of your circuit onsets, or maybe even more optimistically, this might actually happen exponentially. And as a matter of fact, a lot of the numerical studies that have looked at models such as the Heisenberg model or the Fermi-Hubbard model have in fact observed this. Now, they have only observed this for very small instance sizes, but it is then, of course, interesting to understand whether this maybe holds true more generally. Now, this is the question that we set out to answer, and let me give you more of a precise statement in order for the setup. Namely, we'll assume that our Hamiltonian is a 2D lattice Hamiltonian with a ground space that is topologically ordered. So that means we have a ground space that might not be degenerate, could also be unique, but whose entanglement structure contains some form of long-range entanglement. In other words, you need a deep circuit, a polynomial-sized circuit, to actually prepare the ground state of that model. Furthermore, assume that you're preparing the ground state using only geometrically local gates in 2 dimensions. So you're not allowed to use any long-range gates, and you're also not allowed to use any adaptive circuits, okay? These are the constraints. Now, your target is to prepare some state, rho, that has an energy per site of at most epsilon, okay? So we'll just formulate this using the fact that the energy is upper bounded by an epsilon fraction of the global lattice size. And what we're then able to prove is that in the worst case, the depth of the circuit onsets that you require to prepare the state is lower bounded polynomially in the inverse energy density, okay? So in other words, you cannot in general expect for the energy density to decay exponentially with the circuit depth. Now, of course, I formulate this problem in terms of preparing this mixed state, this general state rho, epsilon. What I mean here, of course, is that you have some pure state that is the purification of rho that you're trying to prepare using this unitary circuit, given that you only have a pure product state as an input. Okay, so now let's come to the proof sketch. How did we arrive at this result? Well, it basically follows in 3 separate steps. And the steps are as follows. So the first thing that we do is that we show that you can always find some contiguous subsystem, some patch, call it R, that is a subsystem of the global lattice, on which the low energy state gets arbitrarily close to the local ground space of your system Hamiltonian, okay? So you can always give a lower bound of your choosing to the local overlap that your low energy state has to the ground state of the actual model. Now, this will become important later because then we'll leverage an idea that was introduced by Ha in order to essentially generalize ideas about anion braiding that only apply to degenerate Hamiltonians to the setting where you only have a unique ground state. So we'll generalize some witness function that he defined for topologically ordered systems to our setting where we can use it in such a way that it doesn't apply to ground states, but also to low energy states. And then we shall put upper and lower bounds on this witness function in order to derive our result. And these upper and lower bounds will be as follows. So we'll have some lower bound in terms of the inverse energy density, which will be some polynomial lower bound. And we'll have an upper bound that's also given by a polynomial, but this time in terms of the circuit depth required to prepare your state rho. So it's this relationship then that yields us our circuit depth lower bound, which is simply the square root of the inverse energy density. Okay, so let's dive a bit deeper into these key concepts there. So the first step, of course, as I said, is that we want to show that there always exists a subsystem that has like a high local overlap with your ground state. And essentially, this is pretty easy to show just by saying that, okay, look, take your global lattice, look at any patch R, right? Then you already know, by virtue of having this low energy state epsilon, that globally, your energy per site is upper bounded by epsilon. Now, I can just choose R to be of some arbitrary size, and the energy on this patch simply is epsilon times the size of the patch, okay? So I can just pick a patch with an arbitrary energy, and then I can use ideas around gentle measurements to essentially show that this implies that at least locally on this patch R, I'm actually not too far off from the local ground space. And so this allows us to prove a lower bound on the overlap between the local low energy state, rho, and its projected version onto the local ground state. Okay. So locally, this low energy state, which globally might be completely, might be as far as you like from the ground space, locally, you can get as close as possible, depending on how you choose your patch size R. Why is that important? Well, we'll see in a bit, but first I need to introduce a bit of machinery. And the first bit is this so-called twist product. Now, what is the twist product? The twist product is an algebraic construction that is defined as follows. So imagine you have two operators, P and Q, that can be completely general. For our purposes, it will be easy to consider operators that have a loop-like structure. And the twist product is defined as follows. So imagine you have these two operators, P and Q, and they're supported on some global lattice lambda. Now consider some bipartition M and M complement of this lattice. Then the twist product is as follows. Suppose P and Q are written in some operator Schmidt decomposition. You can always do this using some operator basis for P and for Q on both sides of the partition. Then take their product, but in such a way that across the partition, the order of the product is inverted. Okay? So you're taking P times Q on one half of the lattice, and you're taking Q times P on the other half. Now, why is this interesting? Well, we'll see later. But for example, what this yields, in the case of the toric code, for example, is that if you were to take an X-type stabilizer and a Z-type stabilizer, then their product, their twist product, would simply give you minus their actual product. This is because stabilizers in the toric code are simply single qubit tensor products of Pauli's. And so if you were to take an X-type stabilizer and a Z-type stabilizer of this fashion, and you were to take their twist product, then they would simply overlap at two different points. And you could rewrite them in this way, such that if you pushed X through Z on the lower half of the plane, then this would just equal the product of their stabilizers, but with a minus sign because they clearly anti-commute on that one qubit. Okay. But there is another ingredient that we need to take care of, which is that this twist product only becomes useful to you once these operators satisfy a certain condition with respect to your state. And this condition is called local invisibility. Local invisibility roughly just means that consider some operator P and some state psi. P is locally invisible with respect to psi if, once having acted onto your state psi with your operator P, locally you have not changed the state. Okay? So essentially your operator P is locally invisible with respect to your state if it locally acts as the identity. Now, this particular property seems a bit innocuous and maybe not too important, but it is actually related to properties that we expect for topologically ordered states. And you can then use it in conjunction with the twist product to construct this witness for topological order that I've just been talking about before. In particular, what Ha showed in a paper in 2013 is the following. He proved a lemma that if there is some state psi and you're able to find two operators, P and Q, that are locally invisible with respect to the state psi, then this state will be topologically ordered if their twist product does not factorize into the product of the individual expectation values of the state with respect to these operators. So this is a bona fide witness for the presence of long-range entanglement in its state. Now, This might seem really nice, but there's one difficulty with this concept. Namely, finding these operators in general for an arbitrary state psi is pretty difficult. Like, there's no straightforward, clear-cut way to do this. And one might think that, okay, this method could be used in our case to give us a lower bound for our low energy states. But the problem is simply which operators P and Q should we choose? When can we find operators such that it does not factorize? And the answer is a bit tricky. Namely, what we have to do is we have to come up with some approximate notion of local invisibility to make this framework work for us. So what we do is that we define some, if you like, robust witness function that essentially is just the difference between the left and right-hand side of what I showed you before. And it very much looks like a correlation function, which is why we sometimes refer to it as the twist correlator. Now, what we're then able to show is that you can still use this twist correlator in order to prove a lower bound under the assumption that P and Q are now only approximately locally invisible. So you allow for some relaxation of the local invisibility condition, and you can then save the day just using this approximate twist correlator and the approximate local invisibility condition. Okay, so by approximate local invisibility, I simply mean that now, instead of keeping the state exactly invariant locally, you just slightly perturb it in some bounded fashion. Okay. Any questions so far? Okay, that's good. So, how do we then prove the bound? Well, the proof goes as follows. So now I've said we know that our low energy state locally kind of looks like the Tory code, and we'll exploit that. How? Well, if locally our state on patch R looks like the Tory code, then I know that my stabilizer, my Tory code stabilizer, keeps it stabilized on that patch, right? But it only does so approximately. Why? Well, we're not exactly in the Tory code ground space locally. We are only close by. So we can use the lower bound on the overlap that we derived before on patch R in order to then bound the perturbation that applying a stabilizer onto our lower energy state causes locally on this epsilon good patch R. Okay, so we're then able to derive a bound delta on how approximately locally invisible this Tory code stabilizers are with respect to this low energy state. And so then we can just simply use a Tory code X and a Tory code Z stabilizer, put them onto this epsilon good patch R, bound how much they perturb the low energy state on this patch, and then plug them into our twist correlator. Then we derive lower bounds on the twist correlator in terms of epsilon and an upper bound in terms of D, and voila, we get our main result. And that's it. It's very simple. Okay, so just to wrap up, what we've shown is essentially a no-go result for how efficiently you can prepare these low energy states on near-term devices if you don't have access to VAP circuits. And we've done so for models for which we know that the ground space is topologically ordered. So in models for which we know that you already require deep circuits to prepare the ground state. But even relaxing this problem to just preparing some low energy state proves to be equally hard. Therefore, in general, even though people have numerically observed an exponential decay for the energy per site for a lot of interesting models, like the Heisenberg model or the Fermi-Hubbard model, you can, in general, not expect to see this if your ground space is topologically ordered. Now, on a more somewhat technical side of things, this result might also be interesting to people who are coming from a bit more of a TCS side of things. So there's a lot of excitement recently about the NLTS theorem, which is essentially also a lower bound on the hardness of preparing low energy states of certain more exotic Hamiltonians. So these are not lattice Hamiltonians. They're still local, but they live on like high dimensional graphs. And a key sort of open question in that field is trying to understand whether there's some way of relaxing some of the assumptions around these Hamiltonians. Namely, the proofs that currently exist for the NLTS theorem, they require certain assumptions on the degeneracy of the ground space. They require the ground space to be highly degenerate in order for their proof techniques to work. And so what our contribution here is that at least for the case of lattice Hamiltonians, we find a way of proving circuit depth lower bounds that is independent of the ground space degeneracy. So we find a way of using this by leveraging the Swiss product. It's possible for us to simply look at a ground state independent of its Hamiltonian, and then apply these techniques. So we have essentially Hamiltonian independent technique for deriving circuit depth lower bounds for low energy states. And so, of course, the big open question then is there some way of generalizing our techniques to the setting where you now don't have a lattice Hamiltonian? Okay, and that concludes my talk.
Hi, thanks for the good talk. So we already know that you can't necessarily, I can encode like an NP-hard problem into Hamiltonian, so finding the ground state could be really hard. Can you comment on kind of the overlap of, and okay, the hard part of that is going to be doing some kind of training. Can you comment on the overlap between finding good ground states of things that are going to take a very large amount of training and a long time to descend towards that, and the size of the depth that I need for that? So is it the case that like, I only need poly depth when I have things that I was never going to be able to train to anyway? Or is it the case that there are things which I could train to in poly time, I could only poly many steps to get to, but still need poly depth in my circuit to achieve those ground states?
I don't fully understand the distinction between poly time and poly depth.
So I mean, poly depth, sorry, I'm using poly time to refer to the amount of training steps I have to take, so the number of times I have to run my circuit,
right.
but poly depth is the depth of a particular circuit.
Yeah, so I should say that here we simply assume that the optimization step like happens instantly. We assume that you're given the optimal parameters. Yeah. So this is entirely excluding things like, for example, barren plateau problems or something like that. So we assume that you have access like the optimal parameters for a given ansatz, and that you already have like the optimal ansatz.
Do you have any intuition about like what might be the case? Any ideas?
Probably Samson is the right person to ask there. Let's say. I don't.
Thank you.
Hi.
Oh.
Hi. Very nice talk. Are there any particular constraints on the type of lattices? Like, for example, if you had like some kind of geometrical frustration, does that matter at all, or?
Right. So when you say geometrical frustration, I assume that you mean that if you had a
lattice, Kagome lattice.
Oh, right. No, as long as you're in 2D, you're fine.
Okay.
Yeah. But I should say that our technique itself does not work for frustrated Hamiltonians. I can say, though, that this lower bound should still hold true for those.
Okay, great. Thanks.
Thank you. I have a technical question about this infinity product thing. Does it depend? I mean, it looks like it depends on the bipartition that you choose, but this is not explicit in the notation. So, like, how do you choose it? And like, is it always clear from context, or?
All right, I see. You're right in some sense. The bipartition, like, depending on how your operators look like, the bipartition would make a difference. So you would have to find a twist product for a certain bipartition. In our case, all that matters really for the twist product is that you're separating both intersections of the two operators P and Q.
So, for example, you take the toric code, right? And then you have like the generators of your stabilizers, like weight 4, and they overlap. And then what?
well, all you want is that the 2 points of intersection are separated by the bipartition. That's all you want. Like, otherwise, the twist product is just the same thing as just taking the regular product, if your bipartition doesn't separate the 2 points of intersection.
Yeah, I guess I'm just not familiar with like how you decompose operators into Schmidt decomposition.
For stabilized, this is easy, right? Because they're just tensor product polys.
So it's just one term?
Yeah, literally.
Okay. Okay, thanks.